We will now continue our discussion about scientific truth. In this lecture, we continue to describe the rigorous measurement process, which will define the importance and dictate the format of significant figures in a scientific measurement. We started our discussion about measurements by describing the initial step, which was to first choose an appropriate experimental method. In making this decision, we first thought about an instrument that would match the size of the measurement, and we also wanted to find a measurement that would have the appropriate accuracy and precision. Other factors considered in choosing a method included: how many samples did we want to analyze? How long would it take to do the measurement with this method? How much skill was required to use the method? How complex was the sample? And how many components were in the sample? A second step in the quantitative measurement is acquiring the sample, which is also known as sampling. Sampling can be the most difficult step and the source of greatest error in the measurement process. In chemistry, we usually collect a small amount of material from a much larger source, all the while hoping our tiny sample is a good representation of the bulk material from which it was taken. For example, let's say the sample is the sand on the beach. From this perspective, the beach sand looks homogeneous. A homogeneous mixture is uniform in composition throughout. But another way to define it is a mixture that has the same density at every point. We'll talk about density later. Now, we can't go sampling the whole beach, but we can take a bit of sand from the beach for study. We see as we look closer and closer at the sample of the sand is not homogeneous at all. It is heterogeneous. A heterogeneous mixture is a mixture that is not uniform in composition. This can be problematic, forcing us to take and measure several samples from the source at the beach in an effort to represent the whole beach correctly. The third step involves the proper processing of the sample. This can be a very torturous part of the procedure. Let's look at an example. What if we wanted to measure the amount of caffeine in a particular chocolate bar? Usually, we can't just throw a candy bar into what could be a fragile $250,000 instrument and expect to get meaningful results. So we take the chocolate and carefully process it in an effort to isolate the caffeine before putting it in the instrument. If we're lucky, this processing step can be minimal. An example of a kind of measurement where we don't have to process and isolate everything would be a water sample in which we simply want to measure the pH, either acidity or basicity, of the bulk water. In this case, we just simply put a drop on some pH paper or insert a pH probe directly into the sample. Now that's easy sampling. The fourth step is the elimination of interferences in the measurement. Many times, other chemicals that we're not interested in measuring will be in the sample, and unfortunately, we may have similar physical properties to the chemical we are measuring. These other chemicals might interfere with our measurement, so we will have to figure a way to compensate for this experimental anomaly. For example, when we weigh ourselves on a bathroom scale with our clothes on or even at different times in the day, we will get variability in our actual weight that we need to consider. In the golf analogy from the last lecture, there will be wind and humidity effects that will alter the flight of the ball. In both examples, the interference can't be ignored and must be compensated for when we make the measurement and represent the truth. The fifth step is to calibrate our measuring devices and make measurements, finally. To figure out the length of the shots using various golf clubs, my husband had to spend hours at the driving range where the flag sticks were accurately placed at certain yardages, and he would shoot at them to make sure the combinations of club and force were calibrated before he hit golf balls and shot at the actual golf course. If we wanted to use our bathroom scale correctly, we would first weigh a bunch of material that we knew the exact masses of. These are called controls or standards. From the measurements of these controls, we would produce a plot of data. The actual known mass or weight of our controls would be plotted on the y-axis, and the measured values that were read on the scale would go on the x-axis. It is clear from the data that the correlation is linear, which means that in this example we can fit the data to a line equation. Doing this calculation, the calibration equation is found to be y equals 0.9927, the slope, times x plus 0.4363, the y-intercept. Now, when we take a reading on a scale, let's say the scale reads 147, we can correlate this measurement using our graph, marking the measured value on the x-axis and then reading off the actual weight on the y-axis. Alternatively, we could simply put the measured value of 147 into the linear equation as the x variable, do the math, and find the actual weight by calculating the y variable. Using both methods, we see that our 147 measured value on the scale actually correlates with an actual weight of 146.4 pounds. We now can be much more assured that the value we obtained from our scale can be adjusted to be pretty accurate, representing our true weight. Now let's be real. How many of us do this for our bathroom scales? Most of the time, we just trust that the manufacturer did this calibration for us, don't we? But as a scientist who might be publishing the data for the world to see, and knowing that accurate data is critical in the building and testing of our precious hypotheses, we can't just hope that the manufacturer got it right for us. It is critical that we know for sure that the machine is properly calibrated. Our scientific reputation is on the line. Let's stop for a moment and consider what we have done. Look at all this effort that was required to do the measurement correctly. All these steps were our effort to minimize what we call systematic or deterministic error. This kind of error directly affects the accuracy of the measurement and is error we should be able to identify and fix. In our recent example of the bathroom balance, we could see the presence of systematic error, which we then fixed by calibrating the instrument using controls. Can we find all the systematic error? We hope so, but we can't be 100% sure. That being said, we have a much better chance of being accurate and finding the error, no matter the instrument, if we rigorously work our multi-step measurement process. There is one step left in our measurement process, and it's the calculation of results. It is here where we try to quantify the pesky random error that is always present in scientific measurements. I'll catch up with you in that lecture.